Hello everyone, welcome back. In this section, I'm going to briefly walk you through another example. It is, again, an example we've done in the past because I don't want the focus to be on problem formulation. I don't even want the problem to be on graphing, the focus to be on graphing. Instead, I'd like it to be on our new section, algebraically solving to determine our optimal points, or in other words, our optimal production choices. The Valley Wine Company is a little more complex because there were not one, not two, but 5 constraints, meaning when you graph, there will be 5 different constraint lines. You will also have a lot more unknown optimal points. Any optimal point found on the x or y axis is very easy because both points are given to you. However, if it's not found on one of the axes, then we have to solve algebraically. In this case, because there are 5 constraints, we're going to have a total of 4 unknown points, optimal points, or optimal choices. So let's look at the question now. The Valley Wine Company produces 2 kinds of wine, Valley Nectar and Valley Red. And the wines are produced from 64 tons of grapes the company acquired this season. A 1,000-gallon batch of nectar requires 4 tons of grapes, and a batch of red requires 8 tons. However, production is limited by the availability of only 50 cubic yards of storage space for aging and 120 hours of processing time. A batch of each type of wine requires 5 cubic yards of storage space. The processing time for a batch of nectar is 15 hours, and the processing time for a batch of red is 8 hours. Demand for each type of wine is limited to 7 batches. The profit for a batch of nectar is $9,000, and the profit for a batch of red is $12,000. The company wants to determine the number of 1,000-gallon batches of nectar, X1, and red, X2, to maximize profit. So our first step is highlighting the key information like we've done here to problem formulate. And I've skipped all of the normal things that we go through. Instead, what I've done here is I've come in and I've highlighted right here all of the problem formulation. These are all of the constraints determined from this information. Like I said, we've solved this before, so this shouldn't be a huge leap for you. We have 5 constraints. The first one, 4x1 plus 8x2 is equal to 64. And that is tons of grapes available. We have only 64 tons of grapes. Our second constraint, 15x1 plus 8x2 is less than or equal to 120. And that's the processing time we have available. 5x1 plus 5x2 is equal to 50. And that's the storage time that we have available. Finally, x1 is equal to 7. That's our demand for nectar. And x2 is equal to red, our demand for red. We've skipped all these points because at this point, problem formulation should be relatively easy for you. If in some way problem formulation is not easy, then you should contact me, because we're getting very late. This is week 6 of our course. It's getting to the point where if this is difficult, you should be reaching out to me for help. So once we've done this, once we've formulated our problem, our next step is to graph. And again, because we've already graphed, we've already moved through that section of this course, I've gone ahead and I've skipped the actual graphing. I've drawn our graph. I've entered all of the relevant points here. We can see because there are 5 different constraints, each one of these lines, each one of them represents one of the constraints. I've labeled each of them. C1 is right here. C2 here. C3 here. C4 goes up, and C5 goes across. Oh, this is C5, not C4. That's a small mistake. Now the key here, following the basic ideas that I taught you, allowing x1 to be 0 and finding x2, then allowing x2 to be 0 and finding x1, by following those ideas, those lessons that we've learned, it should be relatively easy to plot all these lines on the graph. Once you've done this, this is where we're moving into unknown territory. This is where we're moving into a new section, or that we covered last time. First and foremost, we highlight our key optimal choices. And because it's a maximization, our optimal choices fall under every line. Mathematically, we know those choices are where two lines intersect. So we're going to see a possible optimal choice here, 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 and finally right here. We're going to have not one, not two, not three like we've seen, but 6 possible optimal choices, as we see here. We have A, B, C, D, E, and F. Each of these could be our perfect, our optimal production choice. Could be 0 nectar, 7 red, could be any of these, could be 7 nectar, 0 red. We don't know yet, but these are the possible choices that we've found. Now, what we do is we write down our known optimal choices, and then we indicate the optimal choices that we have to solve for algebraically. We know point A because we can see it, 0, 7. We know point F because we can see it, 7, 0. But B, C, D, and E aren't known to us. Because they aren't known to us, following the methodology we used last time, we have to solve for each of them. So that's the next step. Step 6, solve for possible optimal choices algebraically. Now this will be a little small because there is a lot of information. I will share this PPT with you. But the first thing we're going to do is we're going to go methodically through points B, C, D, and E, solving as we go. So first one, let's look at point B. Point B we see here is automatically 7. We see where these two lines interact. C1 right here, and C5 right here. So these two interact, and we know C5 is always 7. So we know x2 will be equal to 7. We see that here. Because we have 1 point, it's relatively easy to solve for. We plug x2 equals 7 into constraint C1 or C5. It doesn't matter. But in this situation, we have to use C1 because C5 has no x2 variable, as we can see here. Now, 4x1 plus 8 times 7 equals 64. 4x1 plus 56 equals 64. 4x1 is equal to 64 minus 56. 4x1 is equal to 8. x1 is equal to 2. So what we've done is we've solved for x1. We come up all the way back to here, and we write in we know our optimal choice at point B is now 2, 7, meaning 2 bottles of nectar, 7 bottles of red. Now, we go to point C. Point C we see here is the intersection of two lines. It's the intersection of C3 and the intersection of C1. Because we have no points given, we have to equalize C1 and C3 to eliminate one variable. To equalize, we need x1, we need algebraic transformations. So we can multiply any, as long as we multiply each equation by one number, each part of the equation by the same number, mathematically they remain the same. That's what we've done here. I had 4x1 plus 8x2 equals 64, 5x1 plus 5x2 equals 50. To eliminate x1, I have to multiply the first equation by 5 throughout. To eliminate x1, again, I have to multiply the second equation by 4 throughout. And what we get is 20x1 plus 40x2 is less than or equal to 320. 20x1 plus 20x2 is less than or equal to 200. We subtract, and our x1s are eliminated. So now 40 minus 20, so 20x2. 320 minus 200 is 120. 20x2 is less than or equal to 120. x2 is 120 divided by 20. x2 equals 6. So following this system, just like we did in the last class, you can equalize and eliminate one variable to find the second variable. That's what we've done here. x2 equals 6. So we go up here and we write in that x2 is equal to 6 at point C. Go back down. We plug x2 equals 6 into constraint C1 or C3. It doesn't matter. We work out our problems here. 4x1 plus 8 times 6. We solve and we get x1 is equal to 4. So we come all the way back up and we write in our 4, 6 here. For point D, now we're moving on and we're on our fourth point. Point D, we repeat the same process. We equalize C2 and C3 because that's what's interacting. In this situation, 15x1 plus 8x2 is less than or equal to 120, plus 5x1 plus 5x2 is less than or equal to 50. In this situation, we need to eliminate x1 again. We could eliminate x2, but x1 seems easier. So we are transforming by multiplying each step in this equation by the number 3. And we get 15x1 plus 15x2 less than or equal to 150. And we subtract. What we get here, because we end up with negative numbers, but two negatives cancel, so that's okay. We have, in this situation, minus 7x2 is equal to minus 30. x2 is equal to minus 30 divided by minus 7. x2 is equal to 4.29. So we found our production choice. In this, at point D, we want to produce 4.29 bottles of red. Is this number correct? We're not entirely sure, so let's check our graph. We see here at point D, we come over and we see 4.29 looks pretty correct. Maybe our graph isn't perfect, but essentially this looks to be correct. It's 4.29 looks correct. And we look down here and we see the next one will be between 5 and 6. So let's solve. We plug x2 equals 4.29 into constraint C2 or C3. We do that here, and we get x1 equals 5.71. Very simply, we come over here. We know it's between 5 and 6. 5.71 looks correct. So we take these two coordinates, x1 5.71, x2 4.29. We come up here, and we write them in. Finally, our last unknown possible optimal choice is similar to point B. We see here that at point E, they are interacting. So we know x1 must equal 7 because this is a vertical line at number 7. So it's 7 here. We plug x1 equals 7 into constraint C2. We do that here, and we solve, and we get x2 equals 1.875. So we solve, and these become our possible optimal choices. As we saw last time, because we only had three constraints interacting, we had two optimal choices on the axes, one on the y-axis, one on the x. So it was a relatively simple question. We only had one unknown. In this situation, we have four possible optimal choices that were unknown. So we had to solve for all four right here. Point B, point C, point D, and point E. That's what we've done so far. Following the same steps from before, step 7, we're going to run the possible optimal choices through the objective function to find the true optimal choice. Our objective function was max z equals 9,000 x1 plus 12,000 x2. I haven't written that here. Maybe that was my mistake, just because of simplicity. It wasn't that important to write here, but maybe it was my mistake because I was trying to make things too simple. We do know from solving in the past, though, that it's 9,000 x1 plus 12,000 x2. All I've done here is multiplied 9,000 times all our x1's coordinates plus 12,000 times all our x2 coordinates. And that gives us our profit point at each optimal choice, at each production choice. Because we're trying to maximize, we choose point C, which is the highest value of 108,000. And we know our best possible choice to maximize revenue in this scenario is to manufacture 4x1, 4 bottles of nectar, 6x2, 6 bottles of red. So using the available resources that we have, our best possible choice to make as much money as possible is to manufacture 4 batches of Valley Nectar and 6 batches of Valley Red. Any other production choice would be suboptimal. That's what we want. And that's what we indicate here in our final step. Indicate in natural language the actual optimal production choice that delivers the greatest profit. And we've done that right here. The optimal choice is to manufacture 4 nectar and 6 red to generate 108,000 in profit. This is a more complex example than we did previously, but systematically we follow exactly the same steps and we will get exactly the same answer. Hopefully you have no questions, because part 1 of your homework assignment was solving a 2 constraint problem. In part 2 of your homework, you are going to solve a 3 constraint problem. Now, the key here, or your homework assignment, should be like this when you are finished. I want you to write well. I'm not requiring you to type this because it can be difficult to put on computer. But if you are unable to write legibly, if you are unable to put together a nice, easy to read display like I have here, then I may require you to use the computer. So please When you're preparing your homework, take your time. Use rulers. Write well. Write clearly. Your homework will be 2 pages like this. One for homework problem 1, like this. And one for homework problem 2, like this. Now, your homework, I will tell you how to submit your homework next session. Do not send it to me. Do not submit it. I will give you instructions at the beginning of class next week on how to submit your assignment. Thank you everyone for listening. Without further ado, I will leave you the remainder of the time to begin your homework problem. Here it is. I will leave this on the screen. I will also send this PPT to our group chat to give you an additional guide. Thank you again for listening. Please complete your assignment before our next class, and I will give you instructions on how to submit it then. Thank you again. All right, everyone, as I noted before, I'm going to update this, or I'm going to send this PPT as well. So thank you for listening, and please get your homework finished on time.